Hey, how's it going today? My name is Joey Miyako, and today we're going to use mass spectroscopy and infrared spectroscopy to uncover an unknown structure. Okay, and so first, in order to get started, we're going to start off with infrared spectroscopy. So what infrared spectroscopy is going to be is basically they take this infrared light, they blast it into the molecule, and based on the vibrations across this frequency and wave number, they can tell what functional groups may be present. Okay, they can further break off. This is a great visualization. This is from compoundchem.com, search IR. It's right in there. It's terrific. And this basically tells you where you can expect different functional groups to be present based on where they turn up in your IR. So in starting this up, we can actually separate our IR into 5 different sections, 6 if you include what's known as the fingerprint region. So we're going to start off kind of with an overview, and then we're going to get into the IR of our unknown molecule. So first, we're going to look at zone 1. And zone 1 is typically where we're going to find our alcohols, our amines, our amides, or our alkynes. And the tricky thing with the amides, alcohols, they also may bleed over into zone 2, which is right next to it, but typically zone 1 is where you may see these kind of things. Moving over to zone 2, this is like our 2700 to about 3200. This is where we're going to find our carboxylic acids, we're going to find our aldehydes, we're going to find our alkanes. Okay, which are just our general sp3s. Moving into zone 3, this is where we're going to find our triple bonds, our alkynes, our nitriles, from around 2000, almost 2400, around in that area. Zone 4, this is where we're going to find our carbonyls. So a lot typically goes on in zone 4. I say carbonyls, you got all sorts of stuff. You got ketones, esters, aldehydes, again, carboxylic acids. Because carboxylic acids, as we know, they do have that component that's double bonded, though, even though they have that alcohol group in there too. And then you also have some amide action going on. Zone 5, this is going to be our double bond region. So like our zone 3 had our triple bonds. This is just going to have our double bonds, and we see this with our alkenes and our benzenes, our double bonds between our carbon groups, excuse me. And then our zone 6, our fingerprint region, it's not useful in distinguishing what functional groups are present, but it's really useful in being able to distinguish isomers from each other. So you have 2 people who look alike, but you can tell them apart because they got different fingerprints. Same thing with this. However, there's one thing we got to keep in mind, is that sometimes there will be some big dips, and those could be due to haloalkanes, or these alkyl halide groups, halogens being present in our molecules. So that's definitely something to keep an eye on. So moving on to, this is our IR of our unknown molecule, and this is from SDBS, a Japanese site. Terrific stuff from them. And this is what we got for our unknown molecule. So we're going to go through our 5 groups and fingerprint region, just as we did with that base map out. So looking at zone 1, not really much of anything. Now, like we were saying, alcohols may spill over, amides may spill over a little bit, so we got to keep an eye out for that in zone 2, but nothing really in zone 1. All right, moving into zone 2. All right, now we have this jagged kind of beard shape, okay? And there are 2 things to look at when you're looking at infrared spectroscopy. The first is the position. What zone are you going to be in? And the second is looking at the shape. And in zone 2, you may have this beard shape. This is typical of carboxylic acids. You could have a big down, just a big shoot. That's typically like an alcohol. You could have kind of a fang kind of thing. That's typically like an amide amine. But here we have this beard shape. So this is likely hinting at a carboxylic acid being present in our group. So moving over to zone 3, not really much of anything. That's pretty flat, not much there. Zone 4, we have a really sharp peak, and this is where our double bonds, though, our oxygens are going to be present. Our ketones, our esters, singular double bond oxygen. So definitely, our carbonyl groups. That's definitely probably something with the carbonyl, and this could be indicative, as we know, carboxylic acids. Part of that is the carbonyl. You have the C, you have our OH part, but then you also have our double bond O. So this could be telling for the carboxylic acid. This could be a ketone on its own. We're not sure yet, but this is hinting at what the functional groups could be. Okay, so there may be carbonyl there. Moving on to zone 5, there's pretty much nothing here. Zone 6, our fingerprint region. Again, not the most telling, but because we have these big jagged peaks here, that could point to an alkyl halide of some sort, some kind of halogen present in our molecule. All right, so this is our 3 biggest hints from this infrared spectroscopy of our unknown. This is beard for carboxylic acid, this big dip that may point to a carbonyl, or these big jaggeds that could be a possible alkyl halide. All right, so now we're gonna remember this, and we're gonna move and take this knowledge into our mass spectroscopy. And what mass spectroscopy is basically they take the molecule and they're gonna basically, destroy it into a million different fragments. And these fragments, based on their stabilities, are gonna be present in different amounts after the procedure is done. So, you got peaks here, you got peaks here, you got stuff going on here, you got all sorts of lines. And now what we're going to be able to do is take these different lines along with our knowledge of IR and come up with some possible formula and structure for our molecule. So the first thing we're going to try to figure out is our M+. And our M+ is typically going to be to the right of our base peak, which we will get to next. So hold off a second for there. But our M+ we have here is at 138. Okay, and the first thing we're going to think about is this M+ even or odd? Clearly it's even. If it was odd, that would point to a nitrogen being present. However, it's even, so thankfully we don't have to worry about that. Also, because we have split peaks here, we have 2 peaks. Usually with an M+ you have 1, but we have split peaks, which is again indicative of a halogen being present. We have a 1-to-1, essentially. It's a little different, but it's basically a 1-to-1 ratio, and this actually points to a bromine being present. If it was a 3-to-1, this would point to a chlorine being present. However, it's that 1-to-1 ratio, so this is probably pointing to a BR, which again matches up with our IR that said there's probably a halogen present. So now we're thinking carboxylic acid based on the IR and bromine, again based on the IR and the MS. So as we move to step 2, we're going to find our base peak. This is 94. This is our most stable point, okay, which is why there's the most of it left. Okay, that's the second thing we need to figure out. The third is we are going to try to figure the formula out. So keeping in mind that we have a bromine present, most likely, and a carboxylic acid present, most likely, we can start with our M+, and we can start to subtract the masses of these different atoms away from it. So we'll take our 138, we'll subtract a bromine, the molar mass of a bromine, we'll subtract the molar mass of 2 oxygens, which are present in a carboxylic acid, and subtract the mass of 1 hydrogen, which is on that, that OH, that's the H there. So 138 minus our 79 minus our 32 minus 1, this is going to get us down to 26. Okay, so now after this 26, we know that there's most likely only carbons and hydrogens left. As we saw with our IR, it's most likely there's no more functional groups left. Okay, so now we're going to figure out how many carbons can we get out of 26. Now with a mass of 12, 2 times 12 is 24. So you can likely predict that there's probably 2 carbons left. Now you could say, hey Joey, well, what if there was 1 carbon? Well, in this case, the 1 carbon would lead to 26 minus 12, which would give us 14 hydrogens. It's really unlikely that there are 14 bonds left to be given. But that, with this example, you can pretty much clearly say that there's probably 2 carbons, and then the 2 carbons leaves 2 left over, and this points to 2 hydrogens, which is down to 0. But there's definitely some examples where you can take, maybe you take 1 carbon instead of 2, and you have, 3 or 4 hydrogens left over, or a different number that makes it more plausible. And so it's definitely understood that this is a possible structure, the C2H3BrO2, a possible structure based on the MS so far and the IR. It's possible that there are other ones, but this seems pretty likely. Okay, next we're going to calculate our DOU, which stands for degrees of uncertainty. I apologize. Degrees of unsaturation. And basically, this is going to tell us if there are any carbon rings or if there's any double bonds left. So the formula for this is 2 times carbons plus 2 plus the number of nitrogens minus the number of halogens minus hydrogens over 2. So as you can see, we have 2 carbons, which is going to go here, 3 hydrogens, minus 3, 1 halogen, this 2 is always here, oxygens don't factor in, put it all over 2, that's going to give us 1 double bond or 1 carbon ring group. And as we can remember, we're pretty sure that there is a carboxylic acid, and as we know, the carboxylic acid has a double bond. So this makes sense in the context we're getting a number of 1 here, we have 1 double bond here, starting to get the pieces together. All right, step 5 is putting this all together. Let's get a structure out of this. So we got our formula. We have a good idea of what our functional groups are from both our IR and DOU. With the IR, we think there's a bromide, and we think there's a carboxylic acid. We know there's 1 double bond from the DOU, which again points to that carboxylic acid. We think there's 2 carbons, 2 hydrogens left. Putting this all together, you'd have, let's start with the BR over here. We'll get our carboxylic acid over here. And then we got 2 C's left, 2 H's left, and this is the only place they can go without creating excessive bonds. And this looks pretty good. We got everything checked off. We got these 2 groups. And looking at the structure, here we go. And this is named 2-bromoethanoic acid, or more commonly, bromoacetic acid. So there we go. We use both the tools of MS and IR to distinguish our functional groups and elucidate some sort of structure that could be possible with the information given. Thank you for listening. I hope you have a great rest of the day.